Okay, let us go ahead and get ourselves started today. It's hard to believe there's only just a few days left in class. It's like always like there's so much more to do that I would love to accomplish that we're not going to get done this quarter. But I have thought about like the question you guys posed at the end of last session. Um, if people are interested, I will go ahead and do something over the summertime for people who are looking for classes and want to continue. And if you want to keep on going with this or something like that, you're looking for some summer credit or something like that. So if that's interesting to you, just let me or the TAs know about it because we'll go ahead and put something else together or something like that. Because I don't know, I'm having a lot of fun with this stuff and I want to keep on going. Like, oh, yeah, there's plenty more to kind of keep on going, digging into all this. For today's session, if you haven't done so yet, please go ahead and download from coursework the session 15 examples. There's a bunch of stuff out there that we just uploaded for you. In terms of just thinking about where we are relative to everything, okay, assignment 4 is out called Oh Say Can You See? And it's really all about just visual connectivity between either the sun or to some sort of landmark and really just trying to understand how the faces of your building are relating to some other kind of visual like destination. That's going to be due on Thursday evening, okay, around midnight. We're still going to go ahead and slip in one last little assignment, but it'll be a little assignment in terms of what's going on. Nothing that's going to be major and kind of break you right at the end. So don't panic about that in terms of what's going on. And that'll be due, I'll think about the exact due date on that, whether we're going to do it like at the tail end of the class or going to make it at the beginning of finals week or something like that. We'll allow you some time to get it done. Because it's, but again, the intention is not to kind of load you up with a whole lot of work. Because you guys have been working pretty hard all along. So, yeah, we want to make it kind of finish out nicely for you. In terms of what we're talking about today, let's go back to assignment 4 before we finish with that. You guys have posted some office hours. There's some availability and what's very good. Okay, so today after class and Thursday after class. Very good. Okay. In terms of digging into that, I think many people have dug into different little pieces of it. I've seen different questions floating around. Are there any general questions around it in terms of like what the intent is or what we want you to do? Or is it just pretty much we haven't started yet and questions will arise when we get going? Yes.
Well, for this power, I think it's foresight.
Yes.
And it's like you can't go more than 90 degrees in the one scenario.
Oh, that's just sort of a Revit problem. Yeah.
Figure out if I have to here or whatever, then after a certain moment, that's the end, but it's force error. And you can't copy paste custom notes ever because it takes all that comments that there are.
Oh, very good. Thank you. No, thank you for sharing that. Now, definitely this whole notion about twisting past 360 sort of gets us in trouble.
Yeah. So it should be your 90 if you take the 4 sides.
Okay, for 4 sides then, because then the total amount of twist on the 4 sides together we get to 360. Now, let's take a look at your specific example. I'm wondering if there's a way to fool it, but I don't know. We could take a look at that one. But I think in general, that's the limitation I tend to run into is like anything above 360 sort of gets it in trouble. Although, for the 3-sided tower, I got it to go a little further because I got it to actually to 1200 degrees. It makes me wonder. I don't know. There's just some specific thing. We'll take a look at that. Very good. Okay, in terms of where we are going to be going today, we will continue with all this kind of notion of optimization and thinking about, just modeling different types of towers and different attributes of the towers. So we've been looking at all these things like getting the gross floor area, getting the volume, computing ratios between those things. And last time we looked at the whole notion of trying to consider the directness of a face to something like the sun or to some view that's out in the distance. Today we're going to hopefully expand your options a little bit based on some questions and comments we had last time. What always happens is after class, I always go through and like, you guys plant interesting questions that get me thinking about there has to be a better way to do this. And there always is if you just go digging around on it. So we're going to look at a couple of different ways to hopefully make your life a little bit easier. In terms of what I'll call expanding your optimization options, we're going to look at the whole issue of really grabbing multiple faces and considering multiple faces. Last time we did something which was expedient but felt inefficient in that we grabbed every face individually and looked at it as its own separate node. Okay, but there actually is a way to grab everything and from a whole list of all the different faces, be able to evaluate them all kind of as a group. And that can be very useful. For my little 3-faced tower, it didn't really matter. For the 4-faced tower, it's getting to be more of a pain. By the time I have 8 or 16 or 32 faces, that would be a lot of work in terms of like trying to grab them all individually. So it feels like a nice generalization to be able to go ahead and grab multiple faces, just any number of faces, and be generalizable that way. We're also going to be looking at kind of another thing we might try to optimize, and that's what I'll call the exterior wall floor area. So we have the overall floor area building. There's a particularly prime portion of the floor area, which is the floor area that's adjacent to an exterior window. Okay, so how you actually sort of sort that out, if you really want to be thinking about where all the window offices versus all the offices in the core. And how much window office area have you created? That'll have a lot of different impacts. We can think about that in terms of just kind of being more prime real estate, which might make it more attractive for a developer in terms of that space getting a higher dollar per square foot. But you could also think about that in terms of, just like daylighting or, the energy considerations. The things around the outside surfaces have different values than the things in the core. So you want to be able to isolate that a little bit. Okay. We're then going to switch to an example of what I'll call targeting a value. And what we've been doing so far has been just iterating through a whole lot of different values. We've been doing this for each, where we set up a whole range of values and consider all the different implications of those different values. We're going to try a different approach, which is to use recursion to instead say, what if we were actually trying to focus in on a value? For any geometry, can we get the model to help figure out really how to achieve a target value? Go through and iterate in on that. And we're going to do that by looking at a model of the Freedom Tower, which is actually kind of an interesting geometry, but actually a pretty easy one to work with. So we'll go ahead and take a look at that. So that's where we are going today. Any questions before we dive in? Nope. Sounds good? Okay. Let's go ahead and get started. If you can, head off to example 15.1. Let me give you a little overview of what we're going to do here. In terms of 15.1, this is the way we're going to approach it. We're going to say, hey, we're going to have some sort of tower. We'll start with a little 3-sided tower, but if you want to start with your 4-sided tower, that's okay too. Let's go ahead and just try to get the areas of all the different faces. So what we want to be able to do is first is get the faces. So can we, as opposed to selecting the faces explicitly, just grab the object, grab the family instance, and then from that, go through and explode to create the different faces, get a list of the different faces. Okay. Then, once we go through and we grab all the different faces, you'll often run into a situation where some of the faces are ones that you want to consider, some of the ones are ones that you don't want to consider. For example, in our big twisting tower, I might want to look at the sides, but I don't necessarily want to look at the roof or the ground plane. Okay, so we'll try to filter them out. So we're only considering the faces that we think are interesting. Then we'll go ahead and get some data about each of the different faces. That's going to look pretty similar to what we've been doing so far. We're going to go ahead and use the map function to continue to grab that sun directness value. We'll actually use another function that's a new one called the surface area function, which you guys suggested this last time. If we want to go through and do a little bit of weighting of the different surfaces by the total area of the surface, okay, there's actually a great function, surface area. It'll let us pull the surface area of any individual face, and we can multiply those things together and sum that all up. Okay, so we can sort of get a weighted average. And that's where we're going to go first. Okay, so this would work for the big tower. This would work for a rectangle. It'll work for like whatever kind of surface you want to consider. So I'm going to go ahead and do it with that little twisting tower. But again, go ahead and do this with whatever sort of makes the most sense to you. So I'm going to open up. So I go on out to my examples. In session 15.1. And this will look very similar to what we looked at last time. But again, this would sort of work for another shape. Maybe we'll test it on another shape in just a minute here. So all I really have here, again, is my big conceptual mass. This conceptual mass is divided into a whole series of mass floors. Okay, that won't be critical for what we're about to do to it, but how we did that was, again, just kind of bring in the conceptual mass. We have a whole bunch of different floor levels assigned. Okay, and in that conceptual mass, go back over there again. We've chosen it and just said, let's go ahead and break it into mass floors, where we've checked all the different floor levels. The reason I like to check all the different floor levels is that even if the tower is not as high as the floor levels, if the tower grows to be that high, you know, those new floors will be added automatically. So I could have 160 of them in here, or something like that. Many of them would have an area 0 to them, but just making them all or checking them all off just allows us that if that tower grows or shrinks, you know, it'll go through and have the appropriate number of floor levels to it. Okay, so far we just have this tower, nothing too special going on there. Let's go ahead and just kind of take a look at it. Now, as we were looking at this tower, there were a couple of surfaces that were very interesting to us. There were these, what I considered to be the outer faces of the tower. So let me see if I can grab it here. I'm tabbing. Let's see if I can do it down here. That's so sad. I'm getting all of the mass floors. I can grab it on the side. Making sure it's all turned on. I don't think it is. That should be okay there. It's still there. Might have to open it to grab the individual face. Anyway, I want to grab those faces, the front face, the kind of side face. There's 3 of them around the outsides. Okay, so here's what we're going to do. We're going to, let me go through and open up Dynamo and take a look at the way we did it last time, and we will do it a little bit differently. Okay, if you can, please open up in the Dynamo examples, go to session 15, and within there, grab example 15.1. We'll take a look at that. I'm going to go for the start. We'll kind of build this up organically. Kind of push that over. Push that over a little bit so you can sort of see it all on the screen. Drag that over. Okay, so we have this whole notion of really choosing these individual faces, face 1, 2, and 3. Notice it gives you the same face ID. It actually is the 3 separate faces. That I kind of think of it as a bug, because I would like those to actually be 3 different numbers. But I'm kind of push that over and see if we can kind of show you what I did it again. What I did was I chose change the face. That's not what I want to do. Change the face. Come on over here. I'm going to grab that front face. Change this face. I'm going to go and grab that one. Change that face. I'm going to grab the one that's behind us. Okay. And those actually have about the same surface area right now because this is a very regular tower. But if it was something a little bit different, it would hopefully be like 3 different areas. Okay. In terms of actually choosing or running kind of some very basic analysis on this, you'll see there actually is a surface area function, and it can report the surface area on an individual face. So there's about 53,757 square feet on each of those different faces, and right now they're all even. There's not a whole lot of difference in there. What I want to think about, though, is can I go through and grab those faces, those 3 faces or 4 faces or as many faces as there are on the structure, okay, using the same sort of scripting. So what I can do is set up a series of logic that looks something like this. It all starts with just really selecting a family instance, and from that instance, that's a piece of Revit geometry. And what we want to do is from that actually create a piece of solid geometry. So something that's back in the Dynamo environment as opposed to the Revit environment. So we're going to take that family instance and convert it into what's considered to be a Revit or a Dynamo solid, a geometric solid. And from that, go ahead and pull out some faces. Let's just kind of see if we can see what this looks like. As we choose that triangular mass, the result of the solid from element is just a solid. Okay, so there's a solid representing that piece of geometry. And then we could actually use a function called explode. And explode is all about just basically taking some sort of geometry object and exploding it, okay? And it'll explode it if you give it a solid, it'll explode it into a series of faces. If you give it a list of faces, it'll give you the edges around that face. Okay, so it's kind of a useful kind of just decomposition object or decomposition node. So what it'll do is, if we go through and we feed it that solid, you'll see that it gives us a series of different faces here. So let's see what it gives us. It says there is a planar face, a Hermite face, a Hermite face, a planar face, and a Hermite face. Okay. The planar faces are the top and bottom. Those are things that don't have any curvature to them. Okay, the Hermite faces, those are the ones that are actually sort of formed in that curvaceous kind of structure. For me, it's going to be fairly easy using this one, this specific object, to go through and isolate which are the sides versus which are the top and bottom. You know, if I had another structure that was all planar faces, it would be a little harder to kind of figure out really what is the top and the bottom. You know, we might have to do something else to go ahead and filter those out. But the idea is, what we'd love to do is take this list of 5 different objects here, okay, and go through and just filter it down so only the Hermite faces are considered. So take 5, get it down to 3. Okay, so that's really the next step in all this, is to go through and say, hey, I have some things that I would like to go through and filter, okay, and we could use something called the filter in function. The filter in says, hey, we're going to have a function, okay, that's going to go through and set some criteria, and if it's true, okay, it'll include it. Okay. Filter out would be, if it's true, knock it out of the list. Okay, and there's actually one where filter, whether it's true or false, will make you 2 different lists. Kind of the list if true and the list if false. Okay, so you can use filtering to basically, based on a criteria, go through and either include, exclude, or divide. Okay, so that's what the filter in function is all about. Now the filter in function, what it really takes is just a whole sequence of different objects that you're going to give it to take a look at. And then it looks for something it calls a predicate, which is really just a function which is always going to evaluate to true or false. Okay, so let's take a look at that. We'll grab this guy, we'll take those geometry objects, all 5 of those, and say, great, we're going to bring those in to filter them in. In terms of what the predicate looks like, let's take a look at this function. We have different sorts of functions we can set up to filter by whatever we want. In this case, what I want to do is actually filter just by the type of object. I want to get the planar faces versus the Hermite faces. Okay, so filter items by type is a custom node. Let's take a look at it. All it's really doing is, for all the elements you give it, and a string that we're going to compare it to it, it's going to get the type name, so the name of the type, okay? And then it's going to just compare them and see if they're equal. So in this case, what I'm feeding it is a list of the different elements. The type string that I'm feeding it is Hermite spline. So it's going to see, is the type name equal to Hermite spline? And if it is, it's going to return a true. So this is always either going to return true or false, true if it's equal, false if it's not equal. Now, before we let it go, let me kind of take a look at this get type name. You might wonder about that. That's a custom node too. This is actually a node that's defined in Python. So for any of you who are Python programmers out there and like working with Python, this is really where it all opens up to you in terms of being able to get any access data to anything that's actually in the Revit database underneath us all. So the script that's behind all this looks like this. It's just taking whatever we're giving it and then just getting the type. Getting the type is something that's in the Revit API. There's a function that for anything you give it, you can say get type and it'll return the type. Okay, just a string representing that. So we're getting that, we're casting it into a string, we're putting that as the output. So a very simple Python script that just for anything you give it will return the type. So it'll return, whether it's a Hermite spline or whether it's a piece of furniture or whether it's a wall or a window or whatever it is. This will just grab anything you feed it and ultimately return that type. And that's all it's really doing. Okay, just the barest beginning of a hint though of really like the Python scripting behind this, because there really is a whole scripting language and a whole API which is available. Just really anything in Revit is ultimately available through Python. Okay, and you incorporate it into your scripting just through these nodes, which just really have inputs and outputs. In this case, the in is the input value, the out is what's coming back out. So whatever we fed it is going in as the in, out is just going to, in this case, return that string. Okay, but incredibly powerful. So what filter items by type is going to do is it's going to take, using this filter in, it's like the mapping function. It's going to take all these different items here, say, hey, for each of these different items, is your type equal to a Hermite face? If it's true, super, you're coming through. If it's planar, false, you're not coming through. So the result of all that go ahead and I'll put a little watch on here. It's going to be my filtered list. So all the Hermite faces came through. Again, that would work just the same if I changed it all over here to the planar faces. I get those two faces instead. Okay, let me check in with you in terms of filtering. Sounds interesting, sounds useful, potentially confusing. Think about how we can use that. Okay. So again, just grabbing all those different faces. Now, the example I'm going to use here is going to be fairly easy because I'm just going to grab these Hermite faces, but we'll try this again with some like rectangular objects, see if we can sort of figure out how to make it work for that too. It'll be a little bit different. But once I have those different faces, let's take a look at what we can do. I got faces 1, 2, and 3. Once I filter them in, I know the faces that I want to consider. Okay, I can then go through and compute the values for those different faces. One value we might want to consider is the sun directness for each of those faces. That we've been doing. We know how to do that. We've been playing around with that one for quite a bit. So what I can do is just take all those filtered items and feed them to that function. Okay, that's going to now return a bunch of values for the directness value for each of those 3 different faces. I run that. You'll see there's 3 different values there. Okay, the innovation that was suggested last time, though, is that, hey, we don't just want to sort of consider these values, these average values for the directness on the different faces. We would love to actually go through and consider just sort of some weighting that was by the surface area of each of those different faces. So the surface area function can allow us to do that. We'll go ahead and grab this same list. I'm going to feed it to the surface areas, which will be very boring in this case because they're all the same surface area, but yours will look a little bit different probably. And then what I can do is if I want to kind of have a weighted average, I can multiply those 2 things together and then, maybe divide through, I don't know, we'll figure out what we want to do. So I'm going to grab those weightings I'm going to multiply them by the surface areas. You'll see I get these 3 different values here. These are 3 different multiplied values of the sun directness by the area. So you'll see that, oh, that third surface seems to have the most attraction to it right now. It has the best directness value, so it's scaled up the most to be almost 82,000 square feet. Okay. Out of that, we can decide really what we're going to do, whether we are going to, try to divide through to create some sort of average value for each surface. We can go through, decide whether we want to sum them all up. In this case, what I suggested doing was for the overall shape, just summing it up so that I sort of have, it's the weighted value of each of the different surfaces. I'm summing them all together, so I sort of have the desirability of all 3 of the surfaces added together. And we could all spend a lot of time kind of figuring out the best metric to put those things together, but it's really whichever way you want to. Okay, so we're looking for something that would actually sum things together. I got this list of 3 different items. I would like to sum them all together. It's like one of those strange ones. You go digging around in the hierarchy of all the different things that are available, you'll find sum isn't in there. You sort of want a sum function just to kind of get a list, and it's not in there by default. What I did in that case was, I said, somewhere out there, someone's decided to sum up the list of values sometime before. You know that it's happened at some point. So I did a little search for summing and see what I can find. And we have some different ones in there. We have sum a list. That seems to be a very popular one, installed 152 times. That one looks like Andy Dandy. That one hasn't happened, it's been deprecated, which means that somehow it no longer, it's not working in the preferred way. Okay, so I went with sum list, installed that, and made it available. Now, because I liked it and put it in my function, I actually put it in the same folder. So it's also in the 15.1 example folder. So you can grab it there. But when you're looking for something, some functionality that you don't have by default, and you need to grab it, do some searching. More often than not, you'll find that someone actually has created that functionality. Summing just made too much sense. In terms of how summing actually works, let me just open it up so you can see. Somehow, starting with 0, it's going to add whatever the new value is to that, can ultimately kind of put out a single value for everything there. But I'm going to look at the reduce function, sort of find out exactly what it does. I sort of half understand what this is doing. Reduces a list to a new value by combining each element with accumulated results. Well, that sort of makes sense. That sounds like a nice accumulator to me. This is an example of there's a lot of custom nodes that have functionality that's good to be able to dig into so you can customize it as you need to. Okay, but for the most part, it's all about building kind of a big library of all these things that you can start drawing on and trusting in. So what I'm going to do is take all those different values. Go ahead and run those again. There we go. I have these 3 different values that are multiplied together. And if I want to sum them all up, we run that one more time. That actually sounds like a good, let's take a look at that. Now, you guys are better on some of the math than some of this stuff, but let's kind of take a look at that. So you were suggesting the cross product that would, again, multiply A times B and then add them all together? Let's check it out. I'll buy that. XYZ cross product, or which one? Do you have a cross product function or a Cartesian? The Cartesian product, I think of the cross product, but that's generally for a point. Do you have a function, or which one do you think, Hung? Yeah. You want something that acts like a cross product, right? Yeah, it's all those. In fact, this would be a good function in terms of just giving 2 different lists, multiplying and summing them all together. So if that function hasn't actually been created yet. What we can do, actually, let's see if we can do the surface area of that, mapping that. Let's see if we can make this work. You have a very specific item in mind. You'd love to go ahead and truly kind of take those two things and make them a function. Okay, no worries. That we're going to talk about later, but let's talk about it now because it's actually just equally useful now. If I take those two different nodes, which seem to be doing something very, very useful to me, or for me, let me create a node from the selection. Okay, I'll call this Hong's cross product. Because you're just that famous. So let's see how Hong's cross product works. It takes two different inputs. It multiplies those two different inputs. Okay, and theoretically then gives us a list or sum of all those different items. So if I give that like two lists that are equal in length, and so, with some luck, this should work. So let's see how it actually does. So over here again, if I run this, it's giving us the same value. So a very useful thing. So now that we have Hong's cross product, we could share that freely amongst ourselves and to start creating our own little collection nodes. So if an XYZ cross product won't work, but just a cross product between different columns, super. So be thinking about that. That's actually a really useful way of sharing and ultimately increasing our power, just to continue to go through and create nodes like this. Now, again, Hong's cross product right now is only on my machine at this point. Go ahead and save that away. I'll go ahead and put that in my session 15 examples. Let's talk about the difference between where I can put these things. If I put them, let me cancel all this. If I say save, and I put them in the Dynamo core definitions, they're going to be available to me every time I open Dynamo. They're always going to be hanging around there as CEE 120 things down at the bottom. So it's a good place for things that I'm going to use a whole lot, is to put them down in my core definitions, because then they'll be in my installation. The difference, though, or what you have to watch out for, is they'll be on the machine where you installed it. So if you're on this machine, it'll only be on this machine. For you, it'll be on your laptop, so you'll carry it around. So what I tend to do is I do the inefficient thing, which is I store them in the folder with the example, only because that gets transported around when you grab the example, as opposed to doing them there. But a better strategy in the long would be either to go ahead and put it in your core definitions, or even better, if this is kind of a useful thing, and this actually sounds like kind of a useful thing, Hong can publish this. So you can put it out there in the community, other people can download it, and they can install it in their system too. Okay, so be thinking about that. That's really how we, before I grab interesting things. I'm not sure what I would be doing without get quads from list. Get quads from list was really, really useful. So I kind of owe it to the community to put something out there that's just as useful, back. So think about how you can contribute to. So we now have a function that'll go through and for any list of faces, go through and compute kind of this magic rating. So let's see how that would work for some other cases, though, just to kind of flex it a little bit. So I'm going to go ahead and close up. Let's go ahead and put Hong's cross product up there. Filter items by type. I'll go ahead and save that since I'm now using Hong's cross product. Okay, and let's try this with a different example. So this was actually, pretty straightforward. Well, what worked for us in this case was this shape has such an unusual profile to it that it was kind of relatively easy to figure out which were the faces of interest. Let's kind of approach that a little bit differently. Let me kind of do it with a slightly different model and see if we can still make sense of it. So in that same funny sense, let's go ahead. We could do that with a rectangle. We can do it with a box. Let's see what other sort of interesting things I have on here in terms of some nice conceptual masses, or I can make one. Doesn't look like I have very many masses in here. I'll just make one. I'm going to make a little in-place mass. On level 1. I'm looking at that, wondering why it won't let me draw it there. Let's switch it back over to 3D. Line is too short. That sounds very strange. Draw on the work plane. Oh, I think my cursor's a little odd. I'm going to make a little form out of that. At this point, what can you tell me about my faces? Yeah, I have a bunch of faces in there. Do you think they're all planar at this point? I think they're still all planar. I think that's, it's really not till I add just a little bit of torque to it that it makes one of these Hermite planes. So let's kind of take a look at it this way first. Well, again, open up my add-in. Let's see what I got here. 15.1. I'll do the end. Actually, I'll do that one. That's one we built. Okay, so in the same sense, I can go through and let me select a family instance. Okay, I've got that mass one. Let's run this and take a look at it. Okay, in terms of what we actually created out of all this, it says my list is empty right now, and that is because in my exploded faces, see if I can bring it over here, I have a bunch of planar faces. So right now, since they're all planar faces, filtering on Hermite faces is not doing it for me. So I'd have to filter by planar faces. But I may need something else in terms of really trying to figure out really the faces that I want to consider. Okay, rerunning that, I get a whole lot more faces. Problem is now I'm also considering that roof and I'm considering that floor. So what can we say about them? We have a little just kind of selection problem. We have to figure out a way to get rid of them one way or the other in terms of like, I don't know, just making sure that they're not considered. We can go through and look at the surface area of all of them and say something about the surface area, whether it's less than a certain value. You know, we need some other criteria that's going to really help us try and figure out really what it is that would allow us to filter those. So any suggestions? We're sort of heading off in different territory now. So I don't know, if you look at all those different faces, is there any way we can distinguish that top versus the bottom? We could go ahead and do something like compute surface normals off them or something like that and figure out whether it's going straight up or whether it's going straight down, something like that, and try to filter based on that. And I don't know, let's just think about it, because it's really, you know, could go a lot of different ways, but that's the danger of going this non-explicit route, is we actually do need some criteria for filtering in and filtering out. So we have to think about that and really how we can distinguish that, you know, whether it's area. the truest thing would be to look at some sort of a surface normal to each of these different planes, and from that say that if it's going straight up in Z or if it's going straight down in Z, that would indicate that it's a it's a floor or a roof or something like that, as opposed to a wall. Yeah. That's an interesting one, because then you can just do it by the name of it in terms of doing that. That I don't know. My understanding is I can do all that. I got that surface there. That's comments and mark for that. I don't know if I can actually give it. You'd like to almost just encode in the Revit model somehow, like some distinction, whether that's a wall or a floor or a roof or something like that. And actually, you're onto something though. Because even in terms of that gross floor area, type mark, but I think is that actually just for the surface model? Let me try this. Let's try editing that one in the same sort of way. That's still there. It's really for the whole type, because then it's all. That roof that's considered for the whole type. I want something that's just going to be for the instance. I don't know. Have to work on it. Not sure what it is offhand. We'll figure it out. There's got to be some way that we can go through and distinguish that. But if all else fails, we'll go for something like the surface normals. Okay, let us go ahead and shift gears just a little bit, because we can grab all these multiple areas and work with the multiple areas and compute some rating. That's looking pretty good. Let's take a look at this issue of, well, the surface areas are kind of cool. How can we actually address this whole notion that there's other values we'd like to get, volumes and floor areas, and that's all kind of cool, but there's other interesting stuff we'd like to be able to kind of tabulate too. And for that one, let's take a look at this example. That is, what we'd like to do is actually go through and compute what I'll call the exterior wall floor area. So to do that, what I'm really interested in is this whole notion of that there are some things that are up against the exterior surface, there's some things that are toward the core of the building, and I needed a way to sort of just be able to compute the floor area of like what the difference is. So it's kind of tricky about how you might approach that. Here's one way you could approach that. What I actually did was I needed to come up with a model. What I tried to do is actually come up with a model that would actually reflect that area. So the difference between that outer surface and some inner layer, whether it's 12 feet or 15 feet, whatever you want to consider it away. So I actually created two different masses, something that I called the outer shell and something I called the inner shell. And then using those two different things, I just cut the inner shell out of the outer shell. Okay, and what was left over, that donut-shaped structure, okay, was actually this exterior wall floor area. Okay, and that's something that then we can start tabulating. In terms of getting the floor area, okay, we can go ahead and really grab all of the different mass floors. We can grab the floor area from all of the mass floors and ultimately just add them all up. Okay, so we can go through and filter and then ultimately summarize them. In terms of doing this, though, I needed to, well, I didn't need to strictly for the purpose of summing, but I did it just kind of make the list a little bit neater, saying that, because of what I do of putting a lot more mass floors in than the number of floors that are actually valid, I put a filter in there that says only consider the ones that have a floor area greater than 0. Okay, because it trims the list down and makes it a little bit neater, stuff like that. But something like that is actually an overall good form for doing this type of calculation. And let's see how that's actually implemented. So what you can do is, let me pop out of there. Let me open up instead 15.2, and we'll take a look at that one. Zoom on in there and show you what we have. So here's the deal. We have two different towers actually there. We have an inner tower and we have an outer tower. Okay, let's talk about how we actually created those, because it wasn't actually too bad. Let me look at it from the top. What we started with doing is actually just going through and creating kind of the outer tower. So if I do this twisting tangular, I'll see the outer shell. Let me drag it on in there. I'm just going to put another one in there so you can see what I did. Okay, so that's the outer shell right now. Now I want to have one that's the same, it's just the inner shell. And it turns out the inner and the outer, it's really the same shell. It really just has different dimensions for the radiuses to it. So if you remember on this shell, or on this shape, the two kind of most critical values were, if we keep the rotation the same, it's the top radius and the base radius, because the middle radius we actually just have set up to be the average of those two. It's just sort of evenly split between the two, so it has an even taper. So if I want to go through and create an inner shell, what I can actually do is almost just duplicate this thing, okay? And once I've duplicated it, I can just give it a top radius and a base radius that are smaller, okay? And that'll sort of core it out. So let's see how you can do that. A couple different ways. I could drag in another one and place it ever so carefully. This is a case where I actually like to go through, I will copy, and I will paste something right on top of itself. And it'll complain because it thinks that whenever you're putting things that are exactly coplanar and like a insertion point and just going to be exactly on top of each other, that you're probably making a mistake of some type. But we're going to accept that warning for right now, just as an in-between spot. Now, I can grab one. Doesn't really matter whether I'm grabbing the inner or the outer at this point. They're both labeled outer shell. Okay, either one will work. What I want to do is take one and I want to reduce the top radius from 40 to, let's say, if we consider the boundary of interesting space from the outer windows in, if it was about the size of this room, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's about 20 feet, something like that. So if I reduce the top radius to about 20, then I also reduce the base radius by 20 feet to like 60. Okay. What I actually have now is two different structures. Let me kind of pop that back up into 3D so you can see it. I'll rotate that over so you can sort of see my work a little bit better. So you'll see I have the inner and I have the outer. And if I want to now go through and just compute the difference, what I need to do is cut one away from the other. Okay, I could go ahead and just always be computing the value for the inner and also being outer, then also be computing the value for the inner and subtract them all. Either way, it all kind of works about the same way. It depends on whichever way you prefer to do it. So I could go ahead and get floor area values for the outside and from the inside and just subtract them, and that's a way to do it. Or I can go through and kind of do it on a mass floor basis. It really just kind of depends on really how you want to use the information. You'll see that for this, well, actually there is no mass floor, the floor area right now because we haven't divided into mass floors. Yeah, I'll go out the way of kind of coring it out like a donut, and we'll go that way. But again, this could work a number of different ways. So if I have an inner and an outer, and I want to go through and core it out, what I need to do is use the cut function. The cut function is if you've chosen anything, it hangs around right up there under the Modify tab. We can cut some geometry. When you cut geometry, you either select the first element to be cut or the host. I'm going to choose the outer element because that's the one I'm going to cut. Then what I want to cut with, and that's going to be the inner element. Okay, and now, with any luck, okay, we have this little donut. that's hollow in the center. Okay, now, as we go working, if we rotate and twist, we're going to have to remember to actually twist both different objects because we have to have the inner and the outer kind of twisting together. Okay, we could try and set up some parameters to kind of link those together more integrally. Okay, but now if I want to compute that floor area, what I can do is, again, just grab that guy. Let's just go ahead and grab all the different floor areas, all different levels, turn them all on. Even though I don't have 80 floors, it'll compute a whole series of different mass floors. Now, when I did all this series of mass floors, what I'm going to do now is basically think about tabulating all these different areas. In terms of tabulating all those different areas, the reason I'm going to go after that is that gives me a little more control. You'll see that actually if I just choose the outer surface, okay, it does actually give you a gross floor area, 218,000 plus or minus square feet. Okay, and that's really treating all the floors perfectly equally in terms of what's going on. The reason you might want to go after the mass floors and kind of do them separately is it then starts giving you the ability to kind of consider different mass floors in different ways about whether you want to include them or not. So for example, now for the surfaces you talked about, let's see, could we go through and put a name on them, put some sort of a distinction on them that would actually help us sort out one type for another. And mass floors, I think we have a little more control in terms of doing that. For example, let's think about this. We could go ahead and put in comments, or we can put in a value in here in terms of the mass floors. Okay, so that we actually have some ability to go through and distinguish them. So for example, if this one over here is going to be considered, oh, like a utility space, okay, that has utility, that one doesn't. We have a way of starting to distinguish between them all. Okay, and oh, there's going to be another utility floor down in here. I can spell, right? Okay. This will give us, as we're tabulating, a way to sort of do some sub-distinctions between just all the different floors versus actually being able to kind of say some of the floors have a functionality and tabulate them a little bit differently. Okay, so let's think out how you can actually go through and use this. We got a whole bunch of mass floors. We'd like to add them all up and get the surface area based on some criteria. Let's see what we can come up with. Let us do this. We will go to the add-ins. Let's take a look in there. Let's open 15.2. And I will go for the starting point one. Here's how it basically works. Let me zoom that in for you a little bit. We basically are going to say, hey, we want to grab all the elements in our model of a specific category, and you have to tell it which category. Okay, so there's a big list of standard categories in here, like adapt points, analytical nodes. These are all the different Revit categories. You might recognize a lot of these things are things that show up in visibility graphics. It's just different categories of objects. Okay, so we're going to go for the mass floors. We're going to say, select all the elements of the category mass floor. Okay, that's not so bad. When I run this, you'll see it's going to give you a whole lot of mass floors. Okay, And right now there's about 160 in there. The reason there's 160 in there is because I actually have those two different towers. I have the one and I have the second one that I kind of created off to the side there. Let me go ahead and get rid of one of them just to make it a little bit easier. I'll get rid of this one over here. So if I rerun that again, hopefully there should only be about 80 of them. Why are there still 160? I'm going to think about why that is in a second, because I don't think there should be. It's going to make me wonder for just a minute about why it still has the 160 in there, because I think there should only be 80 in there. Oh well, we'll get to that in a second. Once I go through and grab that big list of all the different elements, I want to grab some sort of area out of there, or data out of there. And for all those mass floors, we can look at sort of what kind of parameters they have available that contain interesting data for us. So for each of those different mass floors, one of the different areas or values that's interesting to me is floor area. Got floor perimeter, exterior surface, floor volume. Let me go for just the floor area. So what I'm doing is just grabbing all those values for floor area. So I'm just taking all those elements and saying, get that parameter for each of them. We'll go through and run that. What's it doing now? It's just here to bother me in terms of, hang on, we're gonna like reconnect some of these things. It's recognizing now that there are some things that got deleted from the database. Let's see if we can kind of like straighten this out in its brain. That's better. So I have a list of 80 different values here. You notice many of them start with 0. And then they go on down from there. Actually, it looks like it's starting from the top of the tower and moving down. So the first whole batch of them are all these just 0, 0, 0, 0, 0. That's because 80 through 50 or something like that are just, there's nothing there. There's no tower in that point. You know, it's only the tower starts at like 50. The top, 30 or whatever just aren't being used right now. In fact, I can even tell you what that is because the top one is 51. Okay, so the top 29 of them probably aren't very useful right now. In terms of going through and grabbing only the valid values, and we can do this a number of different ways. If we just want to add them together again, we could just take all those different values and add them. The zeros just don't matter to us. If I want to do something a little finer, I can go through and start doing some filtering. What I can do is I can either sort that, but that's not really all that consequential. I can just take all those different values as a sequence and say, hey, go through and find all the values greater than 0. Okay. So if I do that, let me take a look at what that node looks like. It's basically if the input value is greater than 0, okay, that's going to return a true. Okay. And when it gets done filtering, let's run that. Hopefully now we'll only have a list of valid values, not those other ones. Okay, so that list now only has 50 of them in there. Okay, and we can go through and sum that up if we like. Oh, that's list length. I don't want to sum the list length. I want to sum the filtered list. Okay, giving me about that 218 in there. Okay, let us do this. Let us go ahead and break right now. Come on back in about 5 minutes. We'll see if we can actually adapt this just a little bit. See if I can actually go ahead and filter out those ones that are the utility levels. That'll be my challenge over the break to see if we can get that to work. So go ahead and come on back in 5, and we will continue and turn our attention to something that looks a little more interesting, something that looks like the Freedom Tower. Yes? Oh, yeah. What it's actually doing is it takes the sequence and then it feeds that in as the inputs. So what the input is the way it works with the map, it works with the filter. You always leave like one open value, and then what it does is it takes whatever you fed to it and it plugs that in as the open value. Does that make sense? So what it's always going to do is, like, there's this list, 10, 20, 30, and it's going to feed it in as input value, and it's going to say, is 10 greater than 0? True or false? Is 20 greater than 0? True or false? So it's going to take that list and apply it one at a time. But that's the part that keeps on changing. Yes. So again, what we were doing is, we were feeding in, like there was always one open thing. And the open thing was, in this case, I'm trying to think, what we were feeding in there with the list of all the different planes, and then filter by type. And then, yes, there always had to be sort of, the face to consider is like the open one, because you want to keep on considering all the different faces. Let me see if I can find that and make that clear, because that's a good question. Let's see. So yes. So the string Hermite face, that got filled in. Input element, since that's open, that'll get each of these different faces that came out of the explode node. So what's going to happen is, let me run it. Actually, I need to select something. It's going to take all the different faces from the explode. The filter in is going to say, okay, type string got filled in, but since input element didn't get filled in, it's going to basically grab the different values of each of the different faces and consider them one at a time. So filter items type is going to always say, for each face, compare it to this type string. Now, weird concept, but it's like very, very like central to a lot of this mapping and all these functions. So, like whenever you leave one thing open and then you apply like a loop construct or some sort of a function construct, it'll go through and try and like evaluate it for each individual case, plugging in the values. Okay, so no, good question.